Hel- Hello friends, today we are going to see Debye modification for heat capacity of solids. I am Dr. Gerald Anthony, Assistant Professor in Chemistry, St. Xavier's College, Palayankotte. So in Debye, consider that solid to be a continuous elastic medium, so the vibration of the atoms could be regarded as a elastic waves propagating through a medium. So he used the term CV in terms of nu. So he found the CV height capacity at constant volume as a uh, function, as a property of a in terms of frequency. So the vibration energy is quantized. So the number of vibrations, that is f of nu, is known to be proportional to the amount of frequencies produced, square of the amount of frequency produced by the elastic medium. Here it can be equated using a proportionality constant alpha star. So there is a wide range of frequency. We are choosing a narrow range of frequency d nu. So the number of vibrations will be given as f of nu d nu. So the number of vibrations can be found using the term f of nu d nu. So here it is given. And also now the total modes of vibration in the crystal is equated to 3n. So here again we are integrating the total number of vibrational frequencies, that is f of nu d nu is equal to 3n. So the limit will be, lower limit will be nu naught and the upper limit will be nu max. So here we are integrating to find the total number of vibrations in this short frequency range. So now we are in, as soon as we integrate the f of nu d nu, so it will be getting nu max cube by 3 as the upper limit, and the lower limit will be nu naught cube by 3. So nu naught will be lowest frequency, which may be considered as 0, so it is omitted. So alpha dash into nu max cube by 3 is equal to 3n. So from this the alpha dash will be, when we see when we can view the alpha dash value in the equation number 3, where 9n by nu max cube will be the alpha dash value. So already we know f of nu is equal to alpha dash nu square. So in that equation we can substitute the alpha dash value from the equation 3. So once we have substituted, we will be getting the f of nu value as such, which is given in the bottom of the slide. F of nu is equal to 9n divided by nu max cube into nu square. So in the Einstein heat capacity of solid, we may know the average energy. So as we know the average energy, so we can substitute that average energy value also in this integration formula to find the total energy. So E is equal to 0 to nu max, integration 0 to nu max with the average energy into f of nu d nu. So we know the f of nu value, which we have found in the previous slide, and you know the E value. The E value is given in the next equation in red color. It is highlighted in the red color font, so you can see E value. We may know it from the Einstein heat capacity of solid. So you please go through the Einstein heat capacity of solid, and then please come and watch this Debye heat capacity of solids. So we are substituting this value h nu by E by h nu by kt minus 1. So we already know Cv is equal to dou E by dou T. So we are already getting the E. We have already applied some formula, and we have got the E value, that is the E value which is present here. So now you have to find the heat capacity of constant volume. So instead of E in this equation, we can substitute the values, that is the integration 0 to nu max h nu by e h nu by kt, this value. Okay, so this value can be substituted here instead of e, and here we have to differentiate this integrated equation. So you should be careful when you are differentiating it. I will explain it in the further slide how to differentiate it. So next, in this above equation, you have to multiply and divide by Kt. K is Boltzmann constant, T is temperature. So in this equation, you have to multiply and divide by Kt. So you have to multiply and divide by Kt. So here you can see I have used the Kt. Kt is appearing in denominator and also in the numerator. So multiplying by and dividing the Kt, you will be getting Kt in the both numerator and denominator. So here you can see Kt in numerator and in denominator. And another thing, already there is n in the equation, the previous equation. So nk is also equal to r. So we have substituted it with r. So nk will be now equal to r. You can consider this as equation number 4a. You side by side, please note down all the equations and you go through the video. So it will be easy for you. As soon as I have substituted some values in the fourth or fifth slide, I will be I have been typed the equation in the second or first slide. So if you have written in the paper, it may be easy for you to follow it up. And next we have now on the next step I have differentiated it. Here you can see in the fourth a equation 4a, there is t in denominator and t in numerator also. Both the t's are get cancelled. So here it will be h nu by k. Next one is you have to differentiate all the other t terms in this equation. Only the t term in the equation. So here you can see I have encircling this e by h nu by kt minus 1 in equation 4a. It is in denominator. Now you have to differentiate it. So whenever you are differentiating it, so as it is in the denominator, if you move it to the numerator, it can be written as e power h nu by kt minus 1 whole power minus 1. As you have already used the formula n into x power n minus 1 in Einstein heat capacity of solids, you have to use the same formula here also. So when you are using it here, it will be converted into minus 2 after differentiation. So when you bring this minus 2 to the denominator, so it will be converted into plus 2. So power plus 2. And the same way, so the h nu by kt, okay, it will be different. E power h nu by kt will be again differentiated, and you can write it as e power h nu by kt in numerator. Again the h nu by kt will be differentiated. So already you will be getting minus 2, sorry, minus 1 e power h nu by kt minus 1 whole power minus 2. Now the h nu by kt will be differentiated. Since the t is in the denominator, when you move it to the numerator, it will be converted into t power minus 1. So minus 1 into t into minus 1 minus 1, that is minus t power minus 2. So what happens when you bring this t power minus 2 to denominator, it will be converted into t square. So already there is a minus in this t and another minus in the e power. So both will be cancelled and the whole equation will become plus. It's the same type of equation which we have carried out, this same type of differentiation in the Einstein's heat capacity of solid. So minus minus will get cancelled. So it will be a positive value. Now you can see. So a positive value is that. So the value for the differentiation value for e power h nu by kt from equation 4a to next equation is in red color. Here these the red color highlighted fonts are the differential answer of this e power h nu by kt minus 1. So as I have already mentioned, so the e power h nu by kt power minus 1, which is in denominator, when it is moved to numerator, it will be converted into e power h nu by kt minus 1 whole power minus 1. When you differentiate it, it will be minus e power h nu by kt power minus 2. In same way, the e power h nu by kt will be differentiated again. So you will be getting a value e power h nu by kt in numerator. Again, h nu by kt will be differentiated individually. So when the h nu by kt is differentiated, so the t is in the denominator, it will move to numerator, it will be t power minus 1. When you are differentiating the t power minus 1, the answer will be minus 1 into t power minus 2. So here also in e power, here also you are having one minus, here also one minus, so minus minus get cancelled. So the my power minus 2, it will be moving to when you are moving it to denominator, power minus 2 will converted into power plus 2. In same way, t power minus 2, which is in numerator, when it is moved to denominator, it will be converted into t square. So here also in numerator it is, so you can see in numerator it will be e power h nu by t power minus 2. So when you move it into the denominator, it will be again plus 2, e power h nu by kt minus 1 power 2. Here also h nu by kt square. So now what happens? The differentiation is over. So now the differential equation is removed. So now you can see the remaining values as C a 9r nu max cube h nu by k nu square d nu e h nu by kt minus 1 power square into e power h nu by kt into h nu by kt square. So already you are here, you are having h nu by k. Here also h nu by k is there, t square is there. When you multiply on the whole, it will become h nu by kt the whole square. So which is the same step was involved in the Einstein heat capacity of solids. Okay. Here you can see the h nu by k has the it has the dimension of temperature when frequency nu is equal to maximum frequency nu max. So the temperature corresponding to this the h nu max by k, since when we consider nu is equal to nu max, so you can simply substitute the nu with nu max. H nu max by k will be the new value. So the temperature which belongs to this H nu max by k is known as Debye temperature theta d. And another important thing, we have done the same substitution in the Einstein heat capacity of solid, where you can substitute H nu by kt with 1. Suppose if you in the previous equation you maybe have some doubt regarding the differentiation, you should not remove the integration, you should have the integration as such, only the differentiation takes place. So the differentiation, if needed, I again explain about the differentiation. So e power h nu by kt, this is for previous equations differentiation answer, minus 1. So it is differentiated as minus 1 e power h nu by kt minus 1 whole power minus 2 into e power h nu by kt. Again the kt h nu by kt square. So here the h nu e power h nu will be reappearing again, and the h nu by kt will be also reappearing in the differentiation form. So you will be getting a minus here for h nu by kt square. This minus get cancelled, so only the whole equation becomes positive. So next one is So here you can see, so then maximum energy E max is equal to h nu by kt. So since we are considering the maximum frequency range, here you are substituting the nu with nu max, so automatically the energy will be also called as E max. Okay, so h nu max by kt. So already we have converted the h nu max by k into theta d. So instead of h nu max by k, you can substitute the value theta d. So the whole equation will become theta d by t. So in equation 6, you can see E max is equal to theta d by t. So already we have an assumption that, so that can be considered as equation 6. You please note down the equation 6. Okay, next one is we have an assumption E is equal to h nu by kt. This is equation 7. And here in this 7 we are keeping the nu at one side, and we are moving all the other variables to opposite side. When you do like that, you will be getting equation 8. So you can see equation 8. Please note down all the equations with the equation number. It will be very much helpful for you. So now you are differentiating that new, when you are differentiating new, so according to equation 9, so that when you are differentiating the equation 8, you will be getting d nu is equal to kt by h is a constant. It will be remaining as such. Only the u get differentiated, that is du. So it is given in the equation 9. In same way, now we are having nu square into d nu. So already we have used the value, nu value, as for nu is equal to kt by h into u, which we have seen in the equation 6, 7, 8. Okay, so now what happens, we are substituting the value of the nu in this equation. So instead of nu square, we are substituting kt by h the whole square u square, and we know the d nu value that is obtained from equation 9. So kt by h du. So nu square by d nu, now we will be getting the value as such. So here already we are having kt by h the whole square, which is in green color font, and another kt by h, it is in red color font. So both will be multiplied and it is converted into kt by h the whole cube into u square du. So equation, this is considered as equation 10. So from equation 6, so in this equation 6, you can find the value of 1 by nu max. Just we are rearranging the equation 6, and you can see 1 by nu max equal to h by kt into t by theta d. Can be cancelled. Now you should again take the equation 5. For easy purpose, I have written the equation 5 again here. So here you can see this is equation 5. In this equation 5, you have to write 7, 8, 9 and 11. All the equations should be substituted. So here you can see, instead of this red color, you can substitute the equation 7. So both red. Next, instead of this nu square, you can substitute the equation number 8. Okay, and also the equation number 9 can be substituted from the green color. So the equation 9 can be used to substitute for, instead of equation d nu. And for nu max cube, 1 by nu max cube, so you can substitute from equation 11. So here you can see, you can go through that equations and you can easily find the values, and you have to substitute the respective values. So when you substitute the respective values, you will be getting the terms as such. So here you can see, so after substitution you are getting the values as such. So the 0 is lower limit, so some type of typing mistake. Okay, typological error. So sorry for that. It should be in lower limit. The u max should be upper limit. Now the limit should be not nu, it is u. So after this you have to convert it into u, because we are substituting, instead of h nu by kt, we are substituting the u, the term u is used. So hereafter you should use the term u max. So now you can see we have, after substitution, you will be having, instead of e power h nu kt, u e power h nu by kt minus 1 the whole square, e power u minus 1 the whole square. And also instead of nu square, you will be getting kt by h the whole cube into u square du, okay, instead of d nu. So everything will be as such when you substitute it. So when you substitute all the values and rearrange it inside the integration terms, you should have only e, u, and other related terms. So remaining all the constant terms are moved away from the integration formula. So now what happens? Here you are having kt cube, here also kt cube, here you are having h cube, here also h cube. So remaining 9r t by theta d the whole cube. So integration now from U max, since the theta d is the Debye temperature which is remaining, so you have to use the term 0 to limit theta d. So e power u, already u square, here also u square, u power 4 du, e power u minus 1 the whole square. So now you have to see the high and low temperature limit the same way which we have done for Einstein heat capacity of solid. So for instead of this term, so instead of this term, you can use the term u square. So since the u value is very small, so the whole e power u, these terms used in the previous equation, can be converted into u square. And also the temperature, when it can be applied, is when temperature is very much lesser than the Debye characteristic temperature. So now instead of that this term in the previous equation, we have substituted the u square. So u square into du. Again, now the limit should be changed into theta d by t. So instead of theta d, you can use the term theta d by t. So this is the because the highest temperature range Debye cutoff frequency will be there. So here you can use the term theta d by t. So when you are integrating this u square, you will be getting u cube by 3. So when you integrating the u square, you will be getting u cube by 3. So already we are having lower limit 0, so the value will be 0. So there is no need for you to consider about lower limit. So when upper limit is used, so you will be getting the answer theta d by t the whole cube into 1 by 3. So as you know the integration formula theta d by t. So instead of u cube, you can substitute the term, the higher limit theta d by t. So whole cube. So in 1 by 3 into theta d by t the whole cube. So that is substituted here. So here you can see the theta d tt the whole cube will be cancelled. Again you will be having 9r into 1 by 3, 3 gets cancelled, cv is equal to 3r. So here you can see only 1 by 3 will be remaining in the integration. So 9r into 1 by 3 is equal to 3r. So the Debye formula has the same high temperature limit as the Einstein equation. So the same Debye equation for lower temperature can be used, that the formula's heat capacity for lower temperature limit will be Cv is equal to alpha dash into Tq. So Cv, that is this value which we have used in the starting point of the derivation. So same thing, same equation is used for low temperature limit. So in the high temperature limit, the Debye equation is so more or less similar to that of the Einstein heat capacity of solid. So the graph will be plotted, and you will be getting the graph as such. So I am unable to draw the graph. Now I am drawing here. So here you can see. So taking CV at y-axis, T theta by D, T by theta D. So you will be getting the graph in such a way. So this the Debye heat capacity of Debye modification of heat capacity of solids or Debye heat capacity of solid is over. Thank you.